Welcome to The Explainer. Today, we are diving headfirst into the very core of how machines learn. We're going to build an intuitive guide for the tools that let algorithms navigate these super complex landscapes of information, specifically by understanding curves and surfaces. These concepts, the derivative and the gradient, they are absolutely fundamental to how deep learning systems get better. And really, getting a feel for them is key.
Okay, so here's the game plan. First, we're going to define the world our AI actually lives in. Then we'll get our hands on a 2D compass, that's the derivative, and figure out how to use it. After that, we're leveling up to a 3D GPS, the gradient, and we'll see how it navigates these tricky surfaces. And finally, we'll look at those situations where our tools can, well, kind of break down. So let's get started.
All right, first things first, we've got to understand the terrain. Before any algorithm can start learning, it's got to have a world to explore, right? And in machine learning, this world, this whole landscape, is all defined by mathematical functions.
The easiest way to think of a function is as a simple little machine. You pop a number in one end, you get a number out the other. And it's consistent. Give it the same input, you'll always get the same output. Now, in 2 dimensions, if you plot the output for every single input, you get a curve. But things get really interesting when our function takes 2 numbers as input, like an x and a y coordinate on the ground, and gives you one output, say the height. Suddenly you're not drawing a line anymore, you're creating a whole 3-dimensional surface, kind of like a sheet fluttering in the wind.
So that's the big question, isn't it? We need tools to find our way around these curves and surfaces, specifically to find the highest highs and the lowest lows. But it turns out, for the methods we're about to talk about to actually work, the functions we use have to play by a few very important rules.
Yeah, our landscape has to be predictable. We can't have any sudden, sharp corners on our path. Those are called cusps. And we definitely can't have any sudden breaks or jumps, which we call discontinuities, where you'd have to magically teleport from one spot to another. We need a path you could trace without ever lifting your pen off the paper.
And another no-no? The path can't fold back on itself. See, if you were to draw a straight vertical line, it would hit the curve in more than one place. That would mean for one single input, there are a bunch of possible outputs. That kind of ambiguity is a huge problem for our navigation tools, so we just avoid it completely. So when you boil it all down, these are the 3 big rules of the road. Our functions have to be continuous, no breaks, they have to be smooth, no sharp corners, and they have to be single-valued, no confusion. These rules guarantee that our landscape is, well-behaved, which means we can always find our way. Okay, let's grab our first tool for the job. We're going to start in the simpler 2-dimensional world of curves. And here, our number 1 tool is the derivative. You can pretty much just think of it as a compass that tells us which way the curve is heading at any exact spot.
So in the world of machine learning, a huge part of the game is cutting down on the system's error. You can actually visualize that error as a curve, just like this one. And our goal, it's to find the absolute lowest point on that curve. That's our global minimum. The highest point, of course, is the global maximum.
Now, trying to find the absolute lowest point on a curve that might go on forever, that can be tough. So to make the search easier, we often just focus on finding local minimums and maximums. Just imagine you're standing on the curve. If you look at just the area immediately around you, the highest point nearby is your local maximum, and the lowest point is your local minimum. Simple as that. Okay, the key to understanding the curve's direction at any single point is something called the tangent line. This visualizes it perfectly. Pick a target point, then pick 2 other points, one on each side, and draw a line through them. Now just slide those 2 points along the curve, closer and closer to your target. The line connecting them is going to shift. Right at that very last moment, just before they all merge, that line becomes the tangent line. It's the one straight line that perfectly captures the curve's direction right at that spot. The ancient Greeks even called it the kissing line, which is pretty cool. And bam, this brings us right to our first huge concept, the derivative. It's really just a fancy name for the slope of that tangent line. That's it. It's just a single number that tells you how steep the curve is and which direction it's going at one specific point. Every point on our curve has its own tangent line, so every point has its own derivative. And here's the really cool part. The value of that derivative tells us everything we need to know. If the tangent line is pointing up, the derivative is positive. If it's pointing down, the derivative is negative. And if the line is perfectly flat, horizontal, then the slope and the derivative is 0. That happens at the very peak of a hill, the bottom of a valley, or on a flat stretch. The derivative is our compass. It tells us which way to go. Okay, so we've got our compass, the derivative.
Now let's actually put it to work and see how we can build a simple little algorithm that automatically finds the lowest or highest points on a curve.
It's actually way simpler than you might think. To climb up to a local maximum, you just follow the sign of the derivative. So we start at some random point, find the slope, and just move in that direction. We take a little step, then we do it again. Calculate the derivative, take another step. We just keep doing that until we hit the peak, where that tangent line goes flat and the derivative hits 0. And that's it, we're there.
And to find a local minimum, which, let's be honest, is usually what we're after when we're trying to minimize error, you just flip the script. You move against the sign of the derivative. So here, we start on the left, the derivative's negative, so the opposite of negative is positive, so we take a step to the right. We just repeat that process, always moving in the opposite direction of the derivative sign until we land smack dab in the bottom of the valley where the derivative is 0.
So that works perfectly for simple 2D curves. But let's be real, most problems in machine learning are way more complicated. They're more like these complex, high-dimensional landscapes. And for that, we're going to need a much more powerful tool.
Welcome to 3 dimensions. This surface is kind of like a big, billowing sheet representing a function that takes 2 inputs. It's a whole landscape of hills and valleys and plateaus. Our simple little derivative compass just isn't going to cut it here. We need to upgrade to a full-blown 3D GPS. And this new tool is called the gradient. So what is the gradient? It's basically a little arrow, what we call a vector. So it has both a direction and a length. Wherever you are standing on this surface, the gradient points you in the one direction that is the absolute steepest way up. It's the path of maximum ascent. And its length tells you just how steep that climb is going to be.
This is such a great way to think about it. Just picture pouring water on the surface. Gravity's going to pull it down, right? And the water will always find the path of steepest descent. It just naturally follows the fastest way downhill. Well, that direction is the exact opposite of the gradient. We call it the negative gradient.
All right, let's put this powerful new tool into action. Now that we have our 3D GPS, the gradient, let's see how an algorithm actually uses it to get around this complex space and find the lowest point.
And this right here, this is the big one. This step-by-step process of calculating the negative gradient and taking a small step in that direction over and over again is the absolute bedrock of all deep learning. It's called gradient descent. You start somewhere, you find the fastest way down, you take a step, and you repeat. You are literally walking down the hill of error until you reach the bottom. But what happens when our shiny new GPS just stops working? This can happen when the ground right under our feet becomes perfectly flat, and there's just no clear direction for up or down. Well, this can happen in a couple of key spots. Whether you're at the very top of a hill, a local maximum, or at the very bottom of a valley, a local minimum, the surface right at that point is basically flat. There is no direction of steepest ascent because everywhere is either flat or downhill. In these spots, the gradient's magnitude just drops to 0. We say the gradient has vanished. It gives you no direction to move. But in 3 or more dimensions, there's another, much trickier spot. It's called a saddle point, and you can picture it exactly like a horse's saddle. From front to back, it curves down, but from side to side, it curves up. So you're simultaneously at the bottom of a valley in one direction and at the top of a ridge in another. And right at the very center of that saddle, the surface is also perfectly flat. The upward curve and the downward curve kind of cancel each other out, so here too the gradient is 0. Our algorithm, just trying to follow the gradient downhill, can get completely stuck. It can't decide which way is actually down. But look, at the end of the day, even with these tricky spots like saddle points, the gradient is still the engine that makes this all go. Just like this quote says, it gives our system precise instructions. It tells the network exactly which of its little internal knobs to turn and by how much in order to take one more step down that hill of error. It is the very mechanism for improvement. So we've totally figured out how to navigate. We've got our compass, our GPS. We know how to find the lowest point in any landscape. But that leads to a brand new and maybe even bigger question. How do we even create this landscape of error? How do we define it and measure it in the first place? Well, we'll dive into that next time. Thanks for joining this explainer.